we're ready to examine the behavior of a closed loop system where we have what's called feedback, meaning that we take the output of our system and then we feed it back into the input. Here we have multiple blocks with different transfer functions, and we have a summing junction, which is actually a comparator. It's going to compare the reference and our output. The procedure for finding the closed loop transfer function is to define a value for whatever comes out of our summing junction, which I'll call E, meaning error signal. The output E is going to be equal to R of S minus Y of S. This is fed into the rest of our system where we know that Y of S is just going to be equal to P, and I'm not going to keep writing the S's over and over again, so I'll just write P times C times E, where we can plug in what we found for E, so we get P times C times R minus Y, and if we collect our terms for Y, we get 1 plus C times P times Y is equal to C times P times R. In other words, Y of S divided by R of S is equal to C times P divided by 1 plus C times P. This is called the closed loop transfer function. The DC gain for the system is defined as the steady state output for a constant unit step input. And we already know how to find that for a differential equation such as this one, where we have y dot plus 0.5y is equal to u of t, where we apply unit step input. And we already said previously that if you have a unit step input or any constant input, that you're going to have a constant final value. And a constant final value means that you can cross out any of the derivatives. And so we know that y is going to head towards 1 over 0.5, in other words 2. That's the DC gain for this differential equation. Let's talk about two other ways to find the DC gain. One is to use the final value theorem. The final value theorem and the Laplace transform says that y as t goes to infinity is equal to the limit as s goes to 0 of s times y of s. Now what's y of s? We already have a transfer function for this system, which was 1 over s plus 0.5, and we are applying a unit step, so that has a transfer function of 1 over s. So basically we just need to take the limit as s goes to infinity, s goes to 0 of s times 1 over s plus 0.5 divided by another s. Those are going to cancel out, so you can see that if you plug in 0, that you get 1 over 0.5 again, therefore verifying what we already saw above. Now, if we're just going to apply unit step and multiply that output by s, then you can see immediately that this is equivalent to just setting s equal to 0 in our transfer function. So we just have to do this in order to find the DC gain from the transfer function itself. This is equivalent to looking at the Bode plot, where if you recall, if we wanted to plot the magnitude, which is the absolute value of h of s plugging in s equals j omega, well, if you plug in omega equals 0, here's the Bode plot, that's equivalent to just going as far to the left as possible on our log omega axis. So this value of m is also going to head towards the DC gain. So there's yet another way to find the system is from the Bode plot itself. We can find the DC gain. Let's do another example of this system where we have a differential equation which yields the transfer function h of s is equal to 4 divided by s squared plus 2s plus 4. If we just use our regular methods, we know that if this is heading towards a constant value, then we cross out the s's and we just get x as heading towards 1, so the DC gain is going to be equal to 1. But we can also use the final value theorem. X of s is equal to h of s multiplied by the unit step function 1 over s, and then we need to take the limit if we want x as t goes to infinity, that's the limit as s goes to 0 of s times x of s, which is just going to be h, plugging in s equals 0. So again, we get a DC gain of 1. And then finally, if we started with the Bode plot of the system, where we have a magnitude and then we have a slope change of -2 that occurs at a corner frequency of 2, then we can just look at the magnitude as frequency goes to 0, and we notice that that magnitude again goes to 1. So the DC gain is what happens to the magnitude for very low frequencies.